Right. So let me welcome everyone to Owen's Defense. First of all, I want to thank Yelena and Adam for joining as committee members. Adam, maybe I should introduce briefly for those who don't know. Adam was a student here some time ago, the inventor of one of the devices that Owen is using in his thesis, and also is currently a staff member at NIST in Boulder, Colorado. So he's joining us on Zoom. So Adam, can you hear me okay?
Yeah. Hey, everybody. How's it going? Happy to be here.
If you want to ask questions, you're probably going to have to yell for us to hear you.
Okay.
And if anyone asks questions, I think we'll repeat them so that Adam can hear. Okay, so it's a real pleasure to introduce Owen today. So Owen joined the group. I'm not going to speculate on the exact date, but some time ago now, as an undergraduate researcher from Wentworth Institute of Technology. And I think it's safe to say that it was sort of halfway through his time at Wentworth where the research bug kind of bit him, and he was inspired to pursue this field. And I think we always imagine that we are imparting knowledge to our students, but I would say that it's very much a two-way relationship with our graduate students. So we learn a lot as much as they do along the way. And one of the things that I think I've been inspired by Owen to change the way I think about my research and my research group is really to think about infrastructure as something that's at least as important for our success as the papers that we put out. So if there was any aspect of the academic world that I think is maybe something that we're not, that maybe doesn't exactly fit with Owen's personality, it's the constant grab for credit, and he's not someone who is really cared one way or the other who gets the credit. He's really focused on making sure that the group and the team moves forward successfully. And so that's something that I've really appreciated about his efforts. He's also done some spectacular technical work on a number of projects over the years. And the one that he kind of landed on, that he really dove into and fell in love with, I think, is the one that you're going to hear about today, which is the it's the first sort of real, I think, viable superconducting memory that I've seen in my career, which now in superconducting electronics, which now spans something like close to 30 years. So I think it's a significant achievement, and look forward to hearing about it.
Thank you, Carl. That's a wonderful introduction and means a lot. I really appreciate it. So thank you all for coming. It's so nice to see so many of you. So I'll get started. I'd like to thank my committee, Professor Carl Berggren. He's been my research advisor for my whole time here, and it's been instrumental in basically teaching me everything I know about research. Joining him on the committee is Professor Owen Medeiros and Dr. Adam McCahon from NIST. And today I'll be defending my thesis titled Superconducting Nanowire Integrated Circuits for Scalable Cryogenic Memory. So since 2018, the amount of energy the United States uses on computation has doubled. And projections estimate that this number could reach upwards of 12% of total US energy consumption by 2028. So this is really driving a big push to move to some lower energy technology, some platform that uses much less energy than what the largest computers today use. For instance, this is the second largest supercomputer in the world, and it consumes about as much energy as a small town when fully running. So the solution people have been thinking about is superconducting electronics. And besides just exascale computing, there's a number of other fields that are converging onto superconducting electronics for the amazing attributes that it has for lower energy operations, as well as faster switching speeds. But with all of this attention, you would think we have a fully scalable superconducting computer, but we don't. And so it kind of raises the question, why don't we have superconducting computers everywhere? The answer to that comes a little bit more clear when we compare the two halves of the von Neumann computing architecture. So if we look at processing, where we look at the energy and delay of different technological platforms, we can see that the superconducting technologies are orders of magnitude better in terms of energy and delay compared to non-superconducting platforms. The story is a little different when we compare that those two in the size and density of memory. So here we're showing that the largest density superconducting memory ever made is around 1 megabit per centimeter squared. And the largest total integrated superconducting memory is only about 4,000 bits. And those numbers are much, much smaller than what we see in conventional semiconducting electronics. And these numbers themselves are even quite old from 2016, so they're likely to be improved. So this leads to the question, how can we improve memory to realize the full capabilities of superconducting electronics? So to do that, to build a fully scalable memory for superconducting electronics, it's important to think how that fits within the full stack of cryogenic computing. So our typical high power refrigeration systems look something like this. And we typically break up different technologies based on the thermal stages. So here at 4.2 Kelvin, we have our superconducting electronics, and those are interfacing with different temperature stages through high density coaxial cables. So if we look more closely at the superconducting electronics, we see all of these pieces that we're very interested in, except for high density memory. And to realize, to make this piece fit, we really need to meet a certain number of requirements. These are based off of studies done to see how can we really scale beyond the largest systems that we've seen. So instead of having our supercomputer consume as much power as a small town, can we make an even larger one and consume even less power? So the two parameters I'm really going to care most about in this talk is the capacity and density. But there's these other properties that are also important for integrating this memory technology into a larger architecture. So how have people approached this in the past? How have they tried to overcome these problems? When you start to look at the field, you notice everybody is using a superconducting loop. And there's a reason for that. If a supercurrent is trapped in a closed loop, it'll persist indefinitely. And it will also not consume any static power. So those two facts make it very exciting for memory applications. The main problem with current demonstrations is here we see the largest demonstration has quite a large cell area. And if we attempt to make that much smaller, we can get to about 1 megabit per centimeter squared in this demonstration by MIT Lincoln Lab, which is the state of the art currently. If people are interested in shrinking even smaller than this 9 by 10 micrometer area, we have a few demonstrations where people have made individual superconducting memories and show that they can be shrunk to much smaller sizes. However, there is no demonstration of these compact cells scaling to larger arrays. So that kind of highlights the two problems we're trying to solve. We need to come up with a memory cell that can be compact as possible, but also one that can be scaled to larger capacity. So how can we scale to larger arrays? So the first problem, in terms of minimizing the footprint, the other demonstrations have had or have run into a real bottleneck based on the flux quantization within superconducting loops. So this expression simply says that there's a certain amount of inductance and current required to trap a magnetic flux within a loop. And if we were to pick a particular current value, which might be based off of our experimental setup, what our current limits are, maybe 50 microamps, we would result in a inductance approximately equal to, say, 40 picohenries. Now, if you're an engineer designer, you take that number, 40 picohenries. Okay, I need to make a loop with that inductance. And typically that inductance is geometric and it's proportional to the size of the loop. So if you shrink down the size of the loop, you also shrink down the inductance. And this is in contrast with the previous statement that we need a certain amount of inductance to trap this flux. Fortunately, that's not the only source of inductance. Superconductors have what's called kinetic inductance, and it's a result of the inertia of the charge carriers in the superconducting condensate. And that scales inversely with shrinking down the cell size. So here, this is the cross-sectional area. And so if we make that cross-section of our superconducting wire, we get more kinetic inductance. So this overcomes that memory inductance bottleneck. In terms of scaling to larger arrays, we're really interested in simplifying the amount of wiring overhead we have. And we'd like to borrow architecture that's familiar to conventional semiconducting memories like DRAM, where we can arrange bits of information in a two-dimensional grid, and each column has a number of bits aligned in series, and we can select a particular row. We can select a particular row using a word line here. Okay. So for the remainder of the talk, I will talk about the scaling limits within superconducting memory and how we overcame them, and eventually demonstrated the largest superconducting nanowire memory with compact storage loops made up of or leveraging kinetic inductance. We'll also talk about how we've overcome a problem that's really persisted with making these devices, which is the overall yield and fidelity of each cell in comparison of one to another. And we'll show that we achieved 99.9% fidelity across all but one cells within an array that looks something like this. And lastly, we'll talk about how this work has resulted in simulation tools that previously did not exist and now will enable us to better understand how this technology will perform when scaled from something like 16 bits to a full system integration with many thousands or millions of bits. So I'll break up this work into three parts, like most device physics works. We can break that up into the design, fabrication, and measurement. So starting with the design, superconducting loops typically might look like this. And if they're drawn symmetrically, the inductance of either branch, left or right, will be equal to one another. And the amount of current through either one of those branches will also be equal. In the past, people have then added ports to direct that current one way or the other, to encode the state that you're trying to remember, either a 1 or a 0 within the direction of that trapped current. But we're looking for a way to reduce the number of ports into a 2-port architecture so we can leverage the row column scaling like conventional memories. So by doing that, we've come up with this asymmetric loop, and that eliminates the need for additional ports to direct the current of the cell. We can perform both operations, write and read from the same port without the need for additional ports. So this is good if we have one cell, and if we want to have more of these cells in series or connect more of them all in the same line, we need a way to select a particular cell out of a given column. So we can do that thermally. We can select a particular cell to a particular bit using a normal metal heater. So we apply some current through this red metallic trace, and that turns our passive superconducting loop now into an active component made up of subcomponents that are thermally dependent upon that enable line. So when we add that heater, we can draw now a unit cell of the circuit diagram of the memory cell, and we can highlight the H-trons, the thermal switches used to select and encode information. And we can see here the red normal metal heater that forms the rows of our array, and the blue superconducting column that forms the columns of the array. And we take this subcircuit and we can put it into a simulation, and we can try to replicate the behavior that we see in the cell. So one thing we might like to do, and we do quite often to check that things are working, is to insert some information like a 1, and then some time later, see if we can recall that information. And we can do the same thing with a 0. And ideally, when we're comparing the two, they should be highly distinguishable. You should be able to tell a 0 from a 1 quite easily. And that's the case here, where we see a large voltage pulse for a 1 and no voltage pulse for a 0. Now, the actual process of trapping magnetic flux within a loop has always seemed a bit like magic to me. So I'd like to try and explain that here. At the top, we have a transient simulation where we're plotting the current through the loop as a function of time. And based on the inductive splitting mentioned earlier, we can plot how the input bias direction flows current down from the top to bottom and splits between the left and right branches. Now, at the beginning of this time window, there is no current in the cell, and at the end of the time window, there is no current in the cell. Now, something interesting might happen when we actually select and enable the device, and we do that with the enable current. And what that does is it lowers the critical current of the cell, and that's visualized here with these dashed lines. So the critical current is the maximum amount that the cell can withstand before turning from a superconductor into a resistive state. And we see here, this blue line attempts to cross that maximum value, and at that point, we form what's known as a hotspot. And this hotspot grows to form a high impedance area, and that high impedance diverts current away from the left branch into the right branch. Then, while the current is flowing through the right branch, all biases are turned off, and we're left with a persistent current trapped in the loop. Now, because the current was flowing from top to bottom, we're left with a persistent current that's rotating clockwise here, and we call that a 1. That can be viewed in the transient simulation, where the current through the right H-tron, shown in red, is positive, and the left H-tron is negative. With this state, we want to make sure that it can survive operations that are solo. So in this case, we are applying only the enable pulse, and it would be pretty bad for operation if just turning on a selection line destroyed our memory state, especially if we're trying to select a different cell per se. So by applying this heater, we reduce the critical current to a particular value, and we want to check to make sure that our persistent current is the same at the beginning and the end. We don't destroy the state. So that's one of the checks we can do in the simulation. So when we have this persistent current circulating and we want to read it out, we apply both signals, the bias and the enable. And in this case, we can see both exceed their maximum value. So the blue and red attempt to cross the dashed lines, and two hotspots are now formed. This large impedance produces a voltage. And we can read that voltage quite easily because it has very high signal to noise based on the high impedance of these hotspots. So that's writing in a 1, and then we read it out and saw a voltage. The opposite can be done, where now if we want to put in a 0, we apply the same pulse, but with an inverse polarity. So now it's a negative pulse. We have the same splitting. The current flows from bottom to top now. We apply the enable again. We see the same switching into the right branch. And when everything is turned off, we have a current now trapped in the opposite circulating direction. Visible here. Now we have blue positive and red is negative. One last check we should do before we check to make sure that the enable, applying the enable by itself didn't destroy the state. We can also try to check to make sure that a large read pulse when not enabled does not destroy the state. So that's done here, where we see a persistent current increased by the read bias. They sum together, and then it remains persistent after. And we have this margin that, if exceeded, would result in an error. So this is one of the things we care about in design, and picking the actual geometry and thickness and other parameters of the cell. So we have our 0 circulating, and now we want to read it out. So just as before, we apply both signals, and this time we only get one hotspot, and we have another margin here between the current flowing through the right H-tron and its maximum value. So this is our margin for reading out the 0 and ensuring we don't see a voltage. If it were to exceed this value, then we'd get a voltage, and the 0 would look like a 1, and that's not a very good memory. So to recap, this is the overall architecture of a single memory cell that we were able to, for the first time, do full transient analysis showing the thermal behavior of the cell. We've also shown how we can simplify the design in needing only 2 ports instead of additional ports for sensing the current. And we've also shown that we can get over the bottleneck imposed by flux quantization by using a material that has a higher kinetic inductance while ignoring the geometric inductance. Moving on, I'll talk about the fabrication process. And I guess one thing to note here is fabricating these devices historically has been quite difficult. We may only have a particular cell within an array working. And this was really a result from the processes that were built at the time, and developing new fabrication processes with a real focus on uniformity and yield has greatly improved the device performance. The fabrication process is shown here. This was all conducted in MIT Nano. I won't go through each step in detail, but it can be broken up into the 4 main lithography steps. So our first step defines pads and alignment markers for making electrical connections. The second defines our superconducting columns. The third defines our dielectric spacer. And the fourth defines our normal metal enable rows. Performing all of this, or performing these steps on a 4-inch wafer, we get this image here. And this particular device contains a number of devices, including single cells, in arrays from 2x2, 4x4, 8x8. And key in this work was also to include a large number of process control monitors. And this was really important in us determining or developing a way of creating a very lightweight simulation tool. So the hotspots shown in the previous simulation are highly nonlinear and are often difficult to solve the full heat equation. So having a simplified behavioral model that's referenced from fabricated and measured data has been really impactful and enabled the simulation results shown earlier. So looking at a zoom in of the actual devices, in the top left is a SEM of the superconducting columns of our memory array. If we zoom in and look more closely, we can see within the 8 columns, we've also defined 8 loops in each column. So this is an 8x8 array. And for reference, we put the previous best state-of-the-art, most dense memory for comparison. So this is the footprint of a single cell, a single bit. In this next image, we pattern on top of a dielectric spacer the normal metal rows, and that defines the 8x8 grid. And zooming in on a particular cell within that, we can see that the alignment between the bottom layer and the top layer is quite good, and this was highly controlled over the full wafer. And we achieved critical dimensions of 100 nanometers reliably over that whole distance as well. So in summary, we've shown how we've realized these devices in practice and developing the processes needed to enable larger arrays, as well as how the information gathered from the process control monitors has really enabled new simulations. So next, I'll move on to cryogenic testing and measurement. Here, I'll try to explain the methods used to first probe the memory to see, are we seeing the expected behavior? Are we able to store information and recall it reliably? Then we also look at what reliably really means, how reliably can we do that? And then we compare how that particular cell might compare to another one to assess our fabrication yield. So our experimental setup is shown there on the left, where we have 2 signals, our input signal and our enable signal. And those 2 signals are delivered to the array at 1.3 Kelvin through some room temperature electronics and coaxial cables thermalized at each temperature stage. We can look at those signals on an oscilloscope. And the 4 here are the write signal, the enable write, our read signal, and our enable read. And by tuning the amplitude of these 4 pulses, we're able to minimize our error rate and try to maximize our margin. In this case, the write amplitude is the same for a 1 or a 0. They just flip the sign. And a read in this case is always positive, and we expect to see a different output based on the state that was encoded in the memory beforehand. So to recap, the memory is a persistent current. To read out the presence of that current, we look at a voltage, and we sample this voltage at a particular time. And if we do this for a sequential number of operations, for instance, writing a 0, reading, writing a 1, and reading, we can tag the voltage for these read operations associated with the preceding written state. So if we tag all of the read 0 values, we can generate this histogram, and we do the same thing for the 1. And we get to understand how distinguishable these 2 states are You can see here they're separated by more than 17 standard deviations, and there's really only a few errors, 9 out of 200,000 write and read cycles. So the way we find this operating point, which seems quite good, is to sweep the different bias parameters. So in this top plot here, we're doing the same process of writing and reading a cell. And we have the interesting behavior of being able to tune the bit error rate from something that approaches 0 to something that approaches 1, shown here with the blue and the red. And so a bit error rate of 1 is actually also a valid mode of operation, as the convention of a 1 being a clockwise or counterclockwise persistent current is a arbitrary choice. So this tunability is a result of changing the temperature using the integrated enable line during the write procedure. So we keep our read procedure fixed, we vary the writing temperature, and we get this output where we can switch what state we're writing to. If we're writing clockwise with a 1 or counterclockwise. This bottom plot shows a similar type of sweep, but instead of changing the temperature during the write operation, we're changing the temperature during the reading operation. And we do this to investigate what value is going to give us the lowest bit error and the widest operating margin. So this red curve here, we can see doesn't approach 0, which is what we want, and it's also quite narrow. However, if we change to some other value, we might get a much more broad region of operation and succinctly or confidently measure 0 errors. So this is done for a large parameter set, really finalizing it down to just those 4 signals I mentioned earlier. Having this experimental data is quite useful. We can compare it to our simulated results. So using our simulator we talked about earlier, we can perform the same operations. So here's the measured data where this time, instead of changing the temperature, we're changing the amplitude of our write pulse. It's somewhat equivalent to storing a different current, as we're seeing here. And we can get the same behavior out of the simulation with reasonable accuracy in the operating margin and the error rate. The transitions in these bottom plots are much sharper than the above plots, as noise was not included in the model. So we really sweep this around and we try to find the most lowest error rate region. And we can do that for a cell, but we can also do that for a large number of cells. And that's what we did for a 16-bit array. So here's the results of performing that type of analysis, writing a particular state, reading it out, and calculating the errors we see. And so the result of all of those measurements are shown here. And we can see that all but one of the devices achieved greater than 99.9% fidelity. Having a working array is exciting and really great. We can look at how much energy we're using to perform those operations. So these are the same 4 pulses we were talking about. And you can see that the signals related to actually encoding the information and supplying a bias to the superconducting column is quite low relative to the large values for the enable signal. And while this is higher than what many people in superconducting electronics have come to expect for energy performance, it's important to remember that these numbers will scale with geometry. So now that we can overcome the scaling limit, we can scale down our devices even smaller. And these numbers are high even for this particular implementation based on the operating temperature of the experiment. And for the enable, this truthfully was a design choice. The material choice of titanium and gold could be replaced with a more energy efficient alternative. Okay, so let's compare how this work has advanced since the beginning. So our previous work is outlined in this dashed gray box. And we can see that we've really pushed the improvement in both the capacity and bit error rate. The other parameters are still in need of improvement, but with an advanced process node, we think that these numbers are easily achievable. And while they don't actually achieve, and even the advanced process node might not achieve the full requirements that we might define for cryogenic memory, we believe that these are suitable enough for a computer architect to overcome with their system of integration and readout. So lastly, I'd like to recap by saying we developed a fully automated measurement setup for characterizing both the bit error rate and operating margins of these devices. We've shown that we can reliably read and write information from these cells within this 4x4 array, and we've demonstrated 99.9% fidelity out of all but one of the cells. So yes, overall, by advancing all three of these, we think we've taken a really positive step in advancing superconducting memory and scaling to larger computing systems and tackling the big problems of reducing the energy consumptions of compute. So now that we have a more suitable cryogenic memory, what can that look like? What will that enable? Well, we can go back to our superconducting stack or cryogenic computing stack. And by adding in our scalable high-density memory, we can now begin to fully take advantage of all of the other impressive gains that have been allotted to us by superconducting electronics. And that is the end of my talk. I would like to jump into some acknowledgements. First and foremost, my research group. Many of them are here. I'm very happy to see all of them. They've all been incredibly supportive, and it's definitely been the best place to be, I would say. Being in a room with everybody smarter than you is really a privilege and a pleasure, to be honest. I'd also really like to thank Dorothy and Rinska for their support in the office and helping over all these years. I'd especially like to thank a lot of the staff that has supported me and other people in all of the research here at MIT that certainly don't get enough credit. So I'd really like to acknowledge them, as well as our collaborators and funding sources. Lastly, I'd like to thank my family and friends. They've been a huge help throughout this entire process, especially my parents, Sandy and Pete, my sister Leslie, who's here, and my grandparents, Harriet and Roland, who are all watching on Zoom. And I'd also like to thank my girlfriend Elizabeth, who's been my other half and the best ever in helping me get through this whole thing. And her family has been very supportive as well, and also very interested in my research, which has been nice. And lastly, my two friends, Dave and Hayden. I hope to get to see more of them soon. Be happy to answer any questions.